Hi everyone, welcome back. Today, we're diving deep into the fascinating world of chemistry to explore a topic that's as intriguing as it is essential: electron affinity. Whether you're a chemistry enthusiast or a student trying to crack the periodic trends, this video is for you. So, let's get started. First, let's understand what electron affinity is. Simply put, it's the energy change when a neutral atom in its gaseous state gains an electron, forming a negatively charged ion. This process can either release energy, which we call exothermic, or require energy, known as endothermic. Electron affinity is typically measured in electron volts or kilojoules per mole. A positive value means energy is released, while a negative value indicates energy is needed. Now here's where things get exciting. Electron affinity shows a pattern as we move across periods and down groups in the periodic table. Across a period from left to right, electron affinity generally increases. Why? Because atoms become smaller, and their nuclear charge increases, attracting incoming electrons more strongly. But when you move down a group, the trend reverses. Larger atoms with more shielding have a weaker pull on incoming electrons, decreasing electron affinity. And of course, like everything in chemistry, there are exceptions. Some of these are due to electron configurations and the shielding effect. When it comes to electron affinity, the size of an atom plays a pivotal role. Let's break it down into two key categories: smaller atoms and larger atoms. Smaller atoms are like powerful magnets for incoming electrons. Why? Because their electrons are closer to the nucleus, where they feel a stronger pull due to a greater effective nuclear charge. This results in a higher electron affinity. Now contrast that with larger atoms. These giants have electrons much farther from the nucleus. The increased distance, combined with the shielding effects of inner electrons, weakens the attraction for incoming electrons. This means their electron affinity is much lower. So, the story of atomic size and electron affinity is one of proximity and attraction. The smaller the atom, the stronger the pull. The larger the atom, the weaker the pull. This simple but powerful trend helps explain why elements behave the way they do in chemical reactions. Let's talk about how the nuclear charge of an atom influences its electron affinity. Nuclear charge refers to the number of protons in the nucleus of an atom, and it has a direct impact on how strongly the nucleus attracts incoming electrons. When the nuclear charge is higher, meaning there are more protons in the nucleus, the attraction for incoming electrons becomes stronger. This results in a higher electron affinity, as the atom is better equipped to capture and hold on to the new electron. On the other hand, a smaller nuclear charge means fewer protons in the nucleus. This weaker pull on incoming electrons results in a lower electron affinity, as the atom struggles to keep the incoming electron bound tightly. So, whether it's a high or low nuclear charge, this fundamental property is a key factor in determining how atoms interact with electrons, and ultimately, how they bond with other atoms in chemical reactions. Let's dive into the screening effect, a fascinating concept that influences electron affinity. Imagine the nucleus of an atom as a powerful magnet, attracting electrons. However, not all electrons feel its pull equally, thanks to something called the screening effect. Inner electrons act as a shield, reducing the nuclear attraction experienced by outer electrons. This is why incoming electrons don't feel the full force of the nucleus. What we call the effective nuclear charge is significantly reduced. The greater the number of inner electrons, the stronger the shielding effect. This means the attraction for incoming electrons is weakened, leading to a lower electron affinity. Atoms with a lot of shielding struggle to hold on to new electrons. But the story changes when there's reduced shielding. Fewer inner electrons mean less interference with the nucleus's pull. As a result, the incoming electron feels a stronger attraction, boosting the atom's electron affinity. To sum it up, the screening effect is all about how much the inner electrons block the nucleus's pull. More shielding means weaker attraction, while less shielding creates a stronger pull on incoming electrons. This balance is critical in understanding electron behavior across the periodic table. Nonmetals, the intriguing members of the periodic table, are highly reactive, and their electron affinity is the key to understanding why. Let's explore how electron affinity plays into the reactivity and bonding nature of these elements. Nonmetals like oxygen, sulfur, and the halogens have exceptionally high electron affinities. This means they're eager to gain electrons, which makes them highly reactive in chemical reactions. Think of them as electron magnets, always ready to form bonds and stabilize themselves. When nonmetals accept electrons, they form negatively charged ions called anions. These ions achieve a stable electron configuration, like noble gases, and are key players in ionic bond formation. For example, chlorine readily accepts an electron to form chloride, contributing to the creation of compounds like sodium chloride. To sum it up, the high electron affinity of nonmetals explains their strong desire to gain electrons. This behavior is central to their reactivity, allowing them to form stable anions and create ionic bonds with other elements. Nonmetals may be small, but their impact on chemistry is immense. Electron affinity is closely linked to oxidizing power, which is an element's ability to gain electrons during a redox reaction. Elements with high electron affinity, such as chlorine, are excellent oxidizing agents because they readily accept electrons to form stable ions. For example, chlorine gains an electron to form chloride ion, a process used in applications like water purification and bleaching. In general, the higher an element's electron affinity, the stronger its oxidizing power, making nonmetals like halogens some of the most powerful oxidizers. Fluorine, despite being the most electronegative element, has a surprisingly lower electron affinity than chlorine. This anomaly is due to fluorine's extremely small atomic size. When an additional electron is added, the compact electron cloud causes strong repulsion between existing electrons and the incoming one, making the process less favorable. This unexpected trend showcases how atomic structure and electron repulsion can influence electron affinity, even overriding general periodic trends. Now, let's take a closer look at the electron affinities in Group 6, the oxygen family, and Group 7, the halogens. You'll notice that halogens tend to have higher electron affinities compared to Group 6 elements. Why is that? It's because halogens are just one electron away from filling their outer shell, which makes them eager to gain an electron and achieve a stable configuration. On the other hand, Group 6 elements, while still eager to gain an electron, have slightly lower electron affinities. This is mainly due to the higher electron repulsion present in their orbitals. So, while both groups want to gain electrons, the halogens are slightly more effective at doing so. To wrap things up, electron affinity plays a key role in understanding chemical reactivity and bonding. It's influenced by several factors, such as atomic size, nuclear charge, and the shielding effect of inner electrons. While periodic trends give us a useful guideline, we also need to keep in mind that there are exceptions. For example, fluorine's electron affinity is a little lower than expected. These exceptions remind us that atomic behavior can be more complex than it first appears.